Matrix, grade 10s, grade 11s, what a pleasure to be with you on Matrix Uploaded. We're really focusing now on the Matrix syllabus because, you know, the grade 10s, you needed to know FX notation and everything, but now we need to give the Matrix a chance because they need this now. Okay, they do a lot more calculus. Okay, but tag along anyway. Let's have a look at an exam question. A tourist travels in a car over a mountainous pass during his trip. The height above sea level of the car after t minutes is given as this cubic equation, and the journey lasts 8 minutes. This is a real-world application of cubic equations and cubic graphs in particular. This one's quite interesting, as you can see. It's a very happy cubic, so it kind of does something like this. It goes up and down and then up again. It's a cubic. So he's traveling, and what we want to do is we want to answer some questions about this. Okay, now let's have a look. There's the equation. The journey lasts 8 minutes. Okay. How high is the car above sea level when it started its journey on the mountainous pass? Okay, let's have a look. Well, look at this. We've got the equation. Now, what happens as it starts its journey? What do we know? Think about it. Have a look here. The time is 0. Time hasn't elapsed. When you start, you're at t equals 0. Time hasn't passed. As he moves with his car, the time is 0. So here we go. So we plug in 0. And he is going to be at 100 meters. How high above sea level? 100 meters above the sea level. Okay, good. Very easy question. S0. No problem with that. Okay, now let's look at the next question. Calculate the car's rate of change. Rate of change of height above the sea level with respect to time. 4 minutes after starting the journey on the mountainous pass. Now, what is rate of change? It's almost like speed if you think of it, the speed of the car. Okay, and what is rate of change? It is a derivative, like derivative slope gradient. Rate of change is like speed. Okay. So what do we know here? Let's have a look. Well, we've got the cubic. Now, a rate of change is a derivative, so you differentiate this. Bring down the 3 and multiply to the 5, 15t squared minus 65 times 2 is 130t plus 200 plus 100. Now that's the rate of change expression. So all we now need to do is plug in the 4 minutes, and let's see what the speed of the car is. Okay, if we plug in 4, it's going minus 80 meters per minute. What does that mean? Well, let's see. So if we look at it in calculus, what does that mean? Minus 80 meters per minute. Well, it says there in number C, interpret your answer to be the height of the car above sea level is decreasing at 80 meters per minute, and the car is traveling downwards. Hence, it is a negative rate of change. Just watch this if I draw a picture here. If you look at this, it's going up and down like that. So what's happening at this stage is the gradient is positive. It's increasing, it's going above sea level, it goes up the pass, now it's coming down the hill. Okay, and then it turns and up we go. Have you got it there? That's a rate of change. Very, very important. Okay, good. Now, the next question is, how many minutes after the journey has started will the rate of change of height with respect to time be a minimum? Let's have a look at this. This is an important principle. If you've got your little graph doing that, this is where the minimum will be. Okay, the minimum is there. Okay, how many minutes after the journey has started will the rate of change be a minimum? Now, the most important principle is when you're at a minimum, the derivative is 0. It's like a turning point of this graph. The derivative is 0. So when we do minimum and maximum problems, the derivative is 0 at a turning point, or at a minimum, the derivative is 0. So what happens here? Let's have a look at this. Okay, so there's your derivative, and we put it, we equal to to naught here. But now the challenge with this thing, guy, it said after how many minutes will the rate of change, this is tricky, the rate of change be a minimum? Okay, so what it's saying now is you must minimize the rate of change. Now, what is the rate of change expression? This is for you guys who are going for an A. You have to differentiate the rate of change, okay, which means you get the second derivative, okay. And this was a bit tricky. So once you get that, remember, we're now not talking about this as the cubic. That would be, when is the rate of change going to be a minimum? They're saying, well, will the rate of change of height with respect to time be a minimum? So you get the second derivative. This is quite a challenge. Okay, so what we do is we put that equal to naught and we solve for t. So the rates of change, the speed will be a minimum at 4,33. Okay, so people, it's quite an important principle, but I want you to focus on a concept here which is important. Okay, don't worry too much about this difficult question with the second derivative. Whenever you minimize or you maximize something, and you're going to see in the next lesson, the derivative is naught. It's like a graph. Now hold on to these concepts. This was quite a challenge one where you had to differentiate the rate of change. The rate of change is a minimum. You differentiate the minimum rate of change. The second derivative is naught. Now stay with us. We're going to pursue something a little bit easier than this in the next lesson on MU. Stay with us.